Okay, welcome back everyone to the Colchian seminar in differential algebra. And today we are very happy to introduce Alexander Demin um, uh, from Russia, who will give a presentation on simple generators of rational function fields and application to structural identifiability.
Thank you very much. Thank you for the nice invitation. So yes, I will speak about this. This is a joint work with Gleb Pogudin, who is from École Polytechnique. All right, so let's begin. I will start with a simple example. Consider a subfield of the field of rational functions in two variables. Let's say the subfield is generated by the following four rational functions. This is a power sums of x1 and x2. Now, these are quite complicated, so maybe we will be willing to find some simple elements in this subfield. And if we have pen and paper, or maybe we have some computer algebra system, we can try to find the following expression. This is an expression of x1, x2 in terms of the original generators. Okay, now if we have a bit more time, we can even find the following. So these are quite complicated expressions, so maybe we won't be able to find them with pencil and paper, but let's say we obtain them somehow. So now these two elements belong to the...
Altogether, this amounts to a simple exercise between Newton's symmetric functions and the classical symmetric functions.
Exactly. So yes, this is a nice exercise. Oh, and by the way, yes, feel free to ask questions and during the talk and yeah, and clarifications. Thank you. So okay, this is nice. Now, since both of them belong to the field and the original generators are symmetric, we conclude that the whole field is actually just the field of symmetric functions in two variables, x1 and x2. And this generating set is quite a bit nicer than the original one. And so not only it is somehow more interpretable, but it also has fewer elements, smaller degrees, and it's quite compact. And this is precisely the question that we will ask in this work. So given some generating set of a field, find another generating set which is simpler. Now, so let me make a small remark. We will not define simple formally. We will consider some perhaps common sense general notion. We would prefer to have few generators, each of them small, sparse, and with small coefficients. Perhaps we'll also ask to avoid redundancy. All right. Now, on the previous slide, I could have written down these formulas. Perhaps it is a known. If I know what to search for, on the previous slide, I could have found these expressions by hand, because I could have guessed them. Here, for example, on this slide, in the following examples, there are more indeterminates. There is no clear symmetries. And we would like to devise an algorithm that given, let's say, such fields, such set of generators, finds some simpler generating set. Now, so just very recently with Gleb, we put online a preprint. So this talk will, so in the preprint, we develop an algorithm. It is an improved version of previous ones to do this. So we develop an algorithm to given such generating set, find a simple one. And later in the end of the talk, I will show you what we obtain, for example, for this particular example in box number 4. So in this talk, I will try to develop the algorithm from scratch that we have obtained with Gleb. First, I will very, very briefly have a digression on theory, then discuss some first algorithms, then some algorithms that we have developed, and then some examples and applications. All right. So first of all, just a very brief digression on theoretical work. First of all, it is kind of a folklore theorem that any such intermediate subfield is finitely generated. So let me remark that in this presentation, the small k would stand for arbitrary effective field. So far, no restrictions on characteristic or some other. So we can assume basically that in this talk, all such subfields are represented by generators G1 through Gm. All right. Now a natural question is how many? That is, how many we can hope to obtain. How many generators we can hope to obtain? And we know that.
So, sorry, Sasha. The field K is fixed once forever, or it will change in the course of your presentation?
For now, it is fixed forever, but in some results, some assumption on it will be required, and I will spell them out.
Okay.
So now, if we know the transcendence degree, we know how many generators we need at least. From the opposite side, we know, of course, that, for example, in characteristic 0, we need at most d plus 1, where d is the transcendence degree. And this is, and kind of a natural question is then posed by Leroth is, can we always use d generators? So is it always enough to use this many generators to represent the field? And this problem has a rich history. We know, for example, for algebraically closed ones, for dimension 1 and 2, the answer is positive. For dimension 3 and more, you can find examples where it's not. And this can be viewed somehow as the very first version of the question we ask. That is, what is the minimal size of the generating set that they can obtain? Now, these are not very algorithmic developments, right? So all of these results are quite are not very effective and probably cannot be turned into an algorithm to actually find this generated set, given some other maybe larger one. But it is still perhaps useful to keep this in mind. All right. Now let me turn into some first algorithms. So the following object will be the main character of this presentation. We will name it by the names of the people who introduced it first, OMS ideal. So we'll consider a subfield in some n indeterminates and introduce another n indeterminates, independent of the previous ones. This OMS ideal will be exactly the following. So we will associate to the field an ideal generated by these guys. And you can note these are exactly polynomials with coefficients from the field that vanish at y equals x. Now, so in this, so let me note, so in this subsection, everything that I talk about is already known. So, and the following theorems that I will present is also known. Our results will come later, and I will explicitly show them. Now, these OMS ideals are useful for characterizing elements of a subfield in the following sense. So if we have such an ideal and we find the reduced Grobner braces of it, and so this will be some polynomials with rational functions as coefficients. Then if we take the coefficients of the Grobner basis and generate field calligraphic f, and calligraphic f will be exactly equal to our original field. So basically, with respect to any monomial ordering, we can compute a reduced Grobner basis, and it will give us an alternative generating set. Now let's just prove this, kind of prove this. I will show. I will tell where it's not exactly a proof. So in one direction, it's quite clear. Computation of Grobner basis does not extend the ground field. And if we start with some polynomials whose coefficients were from our field, and we did some manipulations for Grobner basis, we did not make our ground field larger. Now, in the opposite direction, let's assume that those fields are different. Then pick one element that is in our original, but not in the coefficients of Grobner basis. Let it be G. All right, so we pick this G. Now, the following polynomial belongs to the OMS. So, well, let's say roughly speaking, it vanishes at y equals x, and also its coefficient G belongs to our original field. Here is the why I write proof in quotation marks. Let's assume in this proof, let's assume that G is transcendental. If it's not, we can also work the proof out, but it will be quite longer, and we will need to account for some, we'll need to carefully treat the characteristic non-zero case. For now, let's assume that G is transcendental. Then we know, okay, there exists an automorphism of algebraic closures, so that it leaves calligraphic f the same, but slightly moves G. And so there exists such an automorphism, it slightly moves G. Then we apply this alpha to the polynomials that we had. And it also must belong to the OMS, at least to the ideal generated by the OMS in the algebraic closure. But this new polynomial does not vanish at y equals x, because we shifted G a bit. So, and which is a contradiction. So this is a part of a proof. We also need to account for the case where G is algebraic, but I will not do this here. Okay, so now this could be quite a bit abstract. Let us jump to an example of why these OMS ideals are actually quite nice in our question, the question that we ask. So on the slide, there are two blocks. The first one tells us the set of generators for the OMS ideal. This is a result obtained by Olivier and Müller, Quaid, and Steinwand. And since now we know an original set of generators, and we can compute Grosvenor bases using those, the second block actually does this. So the second block on the slide actually does this for our example. So basically, the first statement tells us that the OMS ideal can be generated by these differences between some polynomial evaluated at new variables minus some polynomial evaluated at old variables, or some versions of those. Okay, so let me walk through the example. we had these power sums, we accept it as input, we produce the OMS ideal, we compute this reduced Grobner basis and obtain almost the results that we had obtained by, let's say, manually. All right, so we know that these coefficients actually generate the field by the theorems that we almost proved on the previous slide. Now, okay, so this is not entirely sufficient to have an algorithm that is actually nice, because note that we have some redundancy here. And so we have some redundancy. In this example, it's trivial to fix this, but in general, not so much. So we would need some way to throw away redundant things that we get. So so before I continue to the full first version of the algorithm, let me also note the following. So the observation that reduced Grobner basis of OMS ideals are useful for simplification in such a way, it was made before, so it's a known result, and it was used before. Okay. Now let me tell you the last ingredient that we need before proposing an algorithm. So we will use it just as a fact. You might be able to see how this follows from the previous things that we discussed, but it's not necessary. We can check if an element belongs to a subfield by just computing normal form with respect to reduced Grobner basis. All right. So this field membership, let's say algorithm, can be used for detecting redundant elements in the set of generators. And so if we know that the generator can be expressed in terms of all others, we can safely throw away the generator. Okay. So now let's say propose or discuss the algorithm, the first algorithm that was proposed by Alexey Ovchinnikov and his collaborators. As in the statement of our problem, we are accepting a set of generators that are maybe huge, complicated, and we want to get back another set that is small and simple. And we will be using OMS ideals here. So we compute the reduced Grobner basis and take its coefficients and use field membership to filter out all redundant ones. And by the practical observations that I noted before, this will produce usually generating sets that are much nicer than the original ones, if it's possible, of course. All right. So in parallel with these developments, there were some other interesting algorithmic developments that are also useful for simplification. Consider, for example, the following specification. And so the algorithm for doing this also existed for quite some time. Given a subfield, we can actually find small degree polynomial elements in the subfield. So basically, the intersection of the subfield with the vector space spanned by monomials up to degree d. And for this can also be framed as a computation with OMS ideals. These are just linear relations in the quotient ring. So, and note that this algorithm in this computation in box 16 can also be used to augment the output of the algorithm by Ovchinnikov and his colleagues. Right, this is because if we can find some simple polynomial elements, this can probably be useful in when we filter out other elements. All right. So far, all right. So these are two, basically, actually three algorithms based on OMS ideals. The first is field membership. Second is finding some simple generating set, and the third one is finding some linear, basically polynomial relations in the subfield. So one first small, let's say, small interesting result that we have in the paper with Gleb is that it is actually not necessary to use elimination orderings when using Rabinovich trick when computing with OMS ideals. And so usually, if you recall, let me go back a bit. So in this definition, we have saturation by some polynomial q of y. And usually in practice, well, typically in practice, it's computed by doing Rabinovich trick and elimination ordering. Now, it is not very convenient, and probably not, and sometimes not very efficient to do this. So we prove that for this particular kind of ideals, you can choose any monomial ordering. So not maybe degree of X or some other practical one. Let me go back. This is the first kind of small, nice piece. All right. Now, but with this algorithm, there are a couple of issues. One wants to actually implement it in practice. And let me discuss now those issues. So we consider an example from the area of structural identifiability, which I will discuss later. For now, we are only interested in this subfield. It is quite large, so the original generating set takes around 2 megabytes to represent on disk. So it's quite sizable for symbolic computation. It has degrees of rational functions up to 34. And in total, there are 249 of those rational functions. Okay. Now, if we use the algorithms described above to compute the reduced Grosvenor basis of OMS, we obtain the following thing. So the variables y here are these new tag variables, let's call them, and variables x are actually the things that we're interested in, these coefficients that generate the field. So, okay, this is amazing. Just by looking at the highlighted coefficients, we deduce that the new simpler generating set will be the following. Now, so we can already note that this computation drastically reduced the size of the generating set, and probably it will be much more convenient to deal with this object in the future. And so we reduce the size from many bytes to just this several sparse things. However, there are a couple of issues. So one of them is that we didn't need the coefficient highlighted in red to produce this result. So the reduced Grosvenor basis contained more than we actually needed. Right? This red coefficient can be expressed in terms of all others, some combination of others. So we didn't actually need it in our simplification problem. And this is more or less kind of tame example, the one that fits on the slide, let's say. There are examples where these redundant coefficients are absolutely huge, but we only need some other very small things. So one first issue with algorithm proposed before is that it computes useless information. Now, of course, the second issue is that computing Grosvenor basis over rational functions is very expensive. So these are these both points are summed up here. Right? So computing over rational functions causes extreme expression swell, especially in many variables. And also we are computing some coefficients that we don't need. All right. So with this, let me go to the next section, how we would try to improve this algorithm. All right. So far what we have discussed were deterministic. It's so the algorithm always produces the same result, always correct. Now we will develop probabilistic algorithms. These are algorithms that may return an incorrect result. We will use the following well-known tool, that if some expression is not zero, then it probably is not zero when we evaluate it at a random point. All right. So, and we will use this to gradually turn the algorithm into the whole algorithm into Monte Carlo. Now, some results were already obtained before us. For example, in characteristic 0 with high probability, and by writing high probability, I will always mean that there is actually a bound that we have. So that user can actually specify the probability of failure. So we know exactly what the probability of failure actually is. And so the first is that we can do field membership probabilistically. The difference with the previous formulation is just one. We just evaluate x at some point. So now for checking membership, instead of computing Grosvenor basis over rational functions and then normal form, we computed just over k. And there are some nice probability bounds based on Schwarz-Zippel lemma, on how exactly to pick the points and how it should work. But this is only for characteristic 0. Now, so second nice result from the paper is the following. So if you recall, previously we had an algorithm that found polynomial relations in the subfield. So relations without denominator. We also adapt this one, this algorithm, to be specialized in Monte Carlo. So we compute, so we specialize X and compute relations among monomials, but now without rational functions. So this is a bit more tricky than previous one, because now if some relation, so relations over rational functions are not exactly relations over the field K, might not be exactly. So there is some interesting correction there that happens and to make algorithm actually viable and yeah. Okay. So this is the first bit that kind of first improvement that we can use. So for this, we also do not need now to compute Grosvenor basis over rational function fields. We only need over field K. Okay, this is great. Now, so we have partially dealt with the problems that we are computing over rational function fields. Now let us deal with the problem that we are computing more coefficients than needed. And the idea here is very simple. Let's just use interpolation and interpolate only those that are potentially useful. So in the examples we had before, we had the following Grosvenor basis. Notice that the degrees of all the blue guys is, well, 1 or 2. The degree of red guy is 4. The interpolation approach would do, let's say, a sensible thing. It would first interpolate the coefficients of degree 1, then of degree 2, and at this moment it would try to notice, okay, that's enough, we don't need to compute more, and we would be done. So just as a side remark, what I mean by actually interpolation is that we evaluate Grosvenor basis at specific points many times, and then we interpolate from these evaluations. We interpolate sparse rational functions. All right. So the new algorithm that we propose is the following. The specification is the same as we have seen before. We accept some large generating set and we produce some smaller one. So basically, the only difference now with respect to previous is that instead of computing the whole Grosvenor basis over rational function field, we circumvent expressions well, and we don't interpolate high degree coefficients by going iteratively. So we compute the Grosvenor basis iteratively. All right. Now there is of course a question of when do we stop? When do we know that we have interpolated enough? Here I have written kind of perhaps vaguely, if there are enough, return them. So during the execution of this algorithm, we of course have access to the input field. We can always check using membership if the original field is the same as the one generated by coefficients interpolated so far. And if so, we hold. So the stopping criteria, so we have a well-defined stopping criteria. Now note that this new algorithm does not need at any point to compute over rational function fields. It always specializes and always uses randomized algorithms. So it always specializes and computes specialized Grosvenor bases. It's the same with membership check. And for this, we have bounds on. So essentially, we allow in the algorithm for the user to provide an epsilon, let's say 10 to minus 18th. And that would be the probability of failure. And the algorithm would pick parameters so that we respect this probability of failure, and we guarantee that we fail with probability no larger than some epsilon. All right. So, yeah, I suppose I can go next. So let's go to the next section. The algorithms that I have showed, we have implemented it in Julia. We tried quite hard to make it practically efficient. We had one application in mind. We wanted to compute some objects in structural identifiability analysis. I will show it later. But of course, I can note that such kind of simplifications are useful not only in particular applications, but also perhaps interesting in general. And so if we can take a generating set that is several megabytes and high degrees and turn it into something very simple in a reasonable time, then this is perhaps of independent interest rather than for some particular application. All right. So now for this part, this is not important to understand in order to understand the whole talk, but I think it would be nice to give the setup of the problems they're interested in. So just to be clear, this is different from the previous part of the talk. This is some application where we actually have these subfields appear. So we'll consider parametric ODE systems with states that are time dependent. We will consider only rational ODEs, only rational ODEs. Here, x of t is a state and mu is some unknown parameter, or many of them. Now, we know that the ideal generated by these combinations of the equations is almost principal. By almost, I mean that, well, let me clarify a bit later what I mean by almost principal. So, okay, by almost principal, I mean that we can compute a minimal polynomial in variable y and its derivatives, but possibly we have discarded some saturation by some polynomial. So there is a minimal polynomial, but modulo some condition. So now if we have a minimal polynomial in y, let's call it h, the interesting thing in the context of structural identifiability is the coefficients of this polynomial, the C1 to Cn. And these are exactly the things that generate the field that we are interested in. So, as you can imagine, such minimal polynomials can be computed using differential elimination. And the results are usually absolutely huge. Right, so that example that I have showed before, where we had like 200 and something generators, it was from this area. So, and our goal, so basically, we want to look at these coefficients and make some conclusions about our original model. But if they're absolutely huge, then it's not possible. And our goal is to simplify them and to make them more interpretable. All right. So this is how we obtain the input for our algorithm. Now let me show some results and some examples. You can find more examples and even more some interesting applications in the paper. Let us look at the table. For example, the first row is the thing that we have seen at the very beginning. And our algorithm successfully computes a simple generating set here, perhaps the simplest possible. The second line in the table is the second example we have seen. So yeah, it has a bit more determinants, has some rational functions. Note that our result is quite simple and concise. Also note that in the original generating set, here R1 and R2, they always appear together. So there is no function where those are separated. Like for example, here R1 and R2 both appear in the function. But in our result, we have deduced that these both belong to the field. So we output them. So there is some, let's say, non-trivial rewriting happening. And there are some other examples. The farm is quite impressive. And so these are absolutely huge sizes of rational functions. It's not possible to look at them for a practitioner and do any conclusions about the model. But our algorithm successfully simplifies this and basically tells us that it is the whole field. So the subfield equals to the whole field. Note actually that these functions, so these linear guys, are not contained in the original generating set. And even more, they always enter as squares in the original generating set. Oh, okay, no, this is I'm sorry, this is wrong. They always enter as polynomials of degree at least 2. Right, so we find some nice linear functions where they were none before. All right, and the last example is also of similar, similarly nice. So now let me say in the last slide just a bit about performance. In the table here, let us look at the highlighted blue row. So this example, MPK5, it has 22 variables, and rational functions are of degree 14 in the original generating set. Now, if we use the very first algorithm that computes the whole Grosvenor basis of the OMS ideal, we would need degree 12. So we would need to compute coefficients of degree 12 and possibly many redundant ones in process in the intermediate expression as well. Now, with interpolation method, we stop after computing just linear coefficients because we can conclude that they generate the field already and we don't need to continue. So we try to be much sharper with respect to the size of the output. Now, so here are there are some more examples in the table. I highlighted the two last ones for the following reason. Okay, so the very last one is kind of interesting. We don't have many examples like that, where the degree of the coefficients in the OMS ideal is so large, like 754. It's quite unusual. But one other reason is that, so for these examples, the Grosvenor basis of OMS ideal cannot be computed by other methods, by any other methods that we tried. For example, by the SlimGB that specifically deals with expressions well and with this kind of problems. So these cannot be computed by direct methods, but with our method, with interpolation, we can. So, and we benchmark our implementation on around 50 examples from the same area and for some others. And so basically we can handle all of them except one where some interesting behavior is exhibited that we don't know much about. So on a data set collected by Villaverde and his colleagues, we handle almost all examples from the data set. Now let me say that our implementation is available online, and the details can be found in the paper, in the preprint. All right. Thank you very much for your attention. Yeah, I'm done.
Thank you very much, Alexander, for this very nice and interesting presentation. Are there any questions from the audience? Please just unmute yourself or write in the chat. So maybe I can start with the question. You presented your algorithm based on substituting a random point for the x variables, right? And then you interpolate and you described, how do you know that you have enough points for your interpolation? So this last check, is it also probabilistic? I mean, you perform a membership test with the original field, right? Is this also done probabilistically?
Yes, this is done probabilistically using also substitutions.
And so when you specify like an error bound in the beginning, this influences how many points A you choose in your loop, but also the membership test, yeah?
So the bound basically affects all steps of the algorithm because all of them are probabilistic.
Yeah.
And each step, so basically bound effects of how large of a range we sample from. So maybe if bound is large, we sample a random point from 0 to a very large integer. Let's say if the bound, so this is how it works. Yeah, it is possible perhaps to do a Las Vegas style algorithm and do the very final check deterministically.
Mm-hmm.
But
Yeah, I was
then it's
thinking along these lines. Yeah.
perhaps less efficient.
Yeah, yeah, sure. Yeah. Okay, are there further questions? Yeah, please go ahead.
Thank you, Sergey.
Okay, let's have a look to the chat. Yeah, so please just unmute yourself or write in the chat if you have any questions or remarks for Alexander. You mentioned at the end your software is available. So we can download this from your webpage or
So there is a GitHub repository,
yeah.
and there is Julia source code of the package. So you can use it as a usual usual package in Julia, and give it some set of generators and get back some simple results. And there are some instructions in the repository. And the link to the repository is in the archive
Yeah,
page.
sure. Okay, no problem. Yeah, great. That's great. Okay, further questions? That does not seem to be the case. Then we thank Alexander again. Thank you very much. And we resume, I think, next week. This is the 20th of February, exactly. We have another talk next week.